gives new pavement full benefits of recycled materials or recycling at the end of life. In other words, since the pavement is recyclable at the end of its life, it will replace the use of virgin materials in another pavement. Therefore, the pavement under study can be rewarded a priori if the rate of recycling is known at the present time. So the cutoff method and the substitution method are the two extremes for the allocation rules that we are using. So a third option sometimes is used, which is the 50-50 method, in which one half of the benefits of recycling are allocated to the pavement using recycled materials, and the other half are allocated to the pavement producing the recyclable materials. And I think the schematics that we have here in front of you in the screen, I guess, illustrate this very clearly. So the common practice when it comes to this here is, when do we need to use the cutoff method? So when we have long-lived products where future recycling is uncertain, that you have a very lengthy life of the pavement, the production may change its properties and deteriorate during its use. So we mostly use this in EPDs and the LCA applications for pavements. On the other hand, the substitution method is kind of like like when you have a short period of time for that pavement, so the life of the pavement is very short, or the inherent properties with use and recycles with recycling do not change that much. So when it comes to the allocations here, some of the LCA recommendations is to provide incentives for practices in order to reduce the environmental impact, a control process to avoid the double counting of credits or emissions of important items, and provide fairness between the different industries who are involved, and that can be reflected through either good calculations or having good estimates. And of course, we need to be transparent so that all parties can understand how allocation is applied and how it's going to be influencing the results. So some simple calculations here. It shows the different scenarios where the materials can be landfilled or used on site or used off-site, or we are reusing it. And the units for this here in particular case is in kilogram. And it shows here in the third column the process that it's included, such as for the landfill that's involved that demolition and transport to the landfill facility. The one for inside, it shows that we're doing recycling process inside. That's include the milling, crushing, and screening. And for offsite, that's going to be including the demolition, but here we need to add the transportation in order to bring it to the central recycling facility. And if we are reusing it, as I mentioned earlier here, that can be by doing it in place, such as when we're doing granulations or any other technique. So this is here, finally, I'm going through a very simple example here where we're trying to show what is the significant role of the end of life here and its impact. For example, for a 5% landfill scenario where we have 95% recycled or reused, as you can see here in the figure on the left, this is the impact of the end of the life on the energy, and on the right you are seeing here the impact on the global warming. For each one of these two figures here, we divided for the cases where it's for asphalt concrete or Portland cement concrete, and each one of here include the three steps here of removal, transport, and landfill. And you can see here for when we dump it in the landfill is maybe something like 40% of the energy and emission. If it's used on off-site, this means that this part is out. And in the following figure here, we're comparing here the end of life compared to the all phases or the 5 phases that I explained or mentioned earlier, which is the material production, the construction, the maintenance, the use, and the end of life. And as you can see here, the largest part here for AC, for example, and the concrete both is the use phase. And the smallest part, which is something like less than 1%, is coming from the end of life. So what I was trying to say here is most of the energy and the emission is related to the use phase, and it will be less to the other phases, but when it comes to the end of life, it is very minimum, and it's 1 or less percent. So with that, thank you. I'll turn it to Kurt.
Thank you, Ahmad. And with that general background, now we want to start looking at some specific end-of-life options for asphalt pavements. And to walk us through that is Dr. Hassan Ozier from the University of Illinois. Hassan?
Well, thank you, Kurt. And I will now continue with the 2 of the end-of-life options for asphalt pavements. And we're going to briefly talk about these 2 options and then provide some sustainability considerations regarding these 2 options. The first option is central plant recycling. I just want to make sure that I can control. Okay, the first option is central plant recycling, and we can categorize central plant recycling into two branches, one of which is the most commonly used one, the hot central plant recycling, which is basically producing RAP for various layers in asphalt pavement applications. And the second one is the cold central plant recycling, which is combining RAP with softening agents to produce mixtures for primarily base or sub-base courses, this is another very commonly applied technique in terms of the end-of-life options as compared to hot central plant recycling. Some of the processes that are included in applying RAP starts with, of course, the removal of existing pavement and transporting this milled pavement layers to a central plant, a central processing facility, which is usually the plants that we produce asphalt mixtures. And in these plants, we crush and screen to obtain different sizes of RAP, which you may see in this pictures can be coarse, and then it can also finer portions of the RAP can be produced as a result of this crushing and screening operations. Some of the sustainability considerations for RAP, I think the most, of course, important sustainability consideration is the performance, pavement performance. How will the pavement performance be affected by the use of recycled materials in our pavements? So in order to improve pavement performance while you're using RAP at the same time, one of the well-known experimentally and then proven techniques are fractionation of RAP and the reduction in the moisture of the RAP stockpiles always are proven to be the techniques that can improve the quality of the pavement products. And improving plant technology to handle higher percentages of RAP is another technique to improve the performance of the asphalt mixtures that contains especially higher contents of RAP. And finally, using softening agents or modifiers if experimentally the performance of these softening agents are promising. And of course, with all that, we have to perform an analysis, an overall life cycle analysis to make sure that the use of RAP is economically and environmental advantageous. So it requires a complete life cycle sustainability evaluation, which may include life cycle cost, life cycle assessment, and a performance assessment in addition to sustainability rating. We often come across a question when to use virgin materials or when to use RAP. So in order to answer such a question, first we have to ask a couple of other questions to ourselves and then be able to answer some of these questions to really come up with an answer. And those critical questions are, can we really achieve an equivalent or better performance with the use of RAP? What is the transportation distance? And does RAP undermine future recyclability? And can we achieve similar target volumetrics, field density in the plant and in the field while we are using higher percentages of REP? And finally, are there any specifications, agency specifications limiting the use of REP? Those are some of the questions that we often ask ourselves to determine when to use virgin or when to use REP in our applications. And just to give you an idea about the environmental impact of hauling, if you consider average transportation intensity of a hauling truck, we get a number like 150 ton miles per gallon, which means we need 1 gallon to transport 150 tons for 1 mile. And if we convert this number to some energy units, if the truck is using diesel and 1 gallon diesel contains 128,000 BTU of energy, which gives us a number like 853 BTU per ton miles, which means we need 853 BTU energy to move 1 ton for 1 mile. What is that really corresponding when we really consider aggregate production energy? So average virgin aggregate production energy, which includes quarrying operations, crushing, screening at a plant, and stockpiling, we can get an average number about 100,000 BTU per ton. So if we do the math, simple math, and then if we find out what is the equivalent distance to aggregate production energy, we find a number like 117 miles. So this is just to give you an idea of how important hauling, transportation of our virgin materials to a job site, so we can easily consume the same amount of energy by transporting more than 100 miles. But of course, this is not enough to really be able to answer the questions that we have asked ourselves. When is environmentally or economically advantageous to use REP? We have to perform a much more complicated and comprehensive analysis. One of this analysis is that life cycle assessment. So this is an example of that shows the relationship between REP and environment from an LCA application. And in this application, we are looking at 11 mixes that are commonly used in Illinois and having various combinations of REP and RES that result in different asphalt binder replacement ABR levels, which is shown in the x-axis of this plot. So we are varying our ABR levels, which means using more REP and RES in those 11 mixes. And we are looking at what are the energy consumption to produce those mixes in the plant. And this only, again, includes the energy production and consumption and greenhouse gas emissions in the plant. So if we look at those numbers, we can clearly see a linear reduction in the energy consumption and greenhouse gases with the increasing use of REP and RES, which is not a surprise for us. But we can also clearly see a distinction between different types of mixes. And SMA mixes are having a higher energy consumption and global warming potential when they compare to a control mix, which doesn't have any REP or RES, and that mix being a hot mix asphalt. So we see clearly whether, regardless of the mix type, SMA or hot mix asphalt, the linear reduction in the production energy and greenhouse gases with the increasing uses of REP and RES. But of course, it's not the only question that we're, I think, seeking answer. We have to look at also the economy and the relationship between the production of costs and the use of REP and RES. We see again a similar trend. In this figure, we have on the left vertical axis we have the ABR percentage, and the x-axis or horizontal axis is the cost of production. And we can see that as the ABR percentages increases, relative cost, which is basically the cost of a production of an asphalt mixture as compared to a control mix which doesn't have any ABR in it, and we are seeing a reduction about 10 to 15% when you are using the highest percentages of REP and RES in the cost of production. And we see similarly again the same shift between SMA and hot mix asphalt materials. SMAs are being more expensive, of course, than the hot mix or warm mix asphalt, but they both also show the similar trend of reduction in the cost when you increase the ABR levels. But we also see in this figure that the energy production is also linearly related to the cost, which I think makes sense because we are calculating basically energy consumption by finding out how much energy consumed or purchased. This energy can be in the form of electricity, diesel or fuel oil that we use in our plants or we use for transportation to the job site. But these are all numbers related to only material and production life cycle. Of course, we know that the payment life cycle is not only about materials and production phases, but we also have to consider the service life phase, which we commonly refer as use phase. So if you consider all of the phases of life cycles, what we can expect from the use of recycled materials in our payments, and the material acquisition and production phase, since we are replacing virgin, binder, and aggregates, we can expect a saving and the energy consumption or greenhouse gases. But we may expect potential increases in the plant energy consumption, which may be a negative for the energy and environmental impacts. During the construction, if the same workability is achieved, we may not expect any changes in the environmental impact for the mixes contain recycled content. And in the maintenance and rehabilitation stage, in case of payment performance reduction, the more frequent rehabilitations are expected, and if that happens, then we may expect a reduction in the environmental increase in the energy consumption or emissions with the use of recycled content. And finally, for the use phase, in the case of pavement performance reduction, with the additional vehicle operations or fuel consumption, we may expect a negative impact of for the payments constructed with higher percentages of recycled content. So this is giving a general overview of what we should expect for some of the scenarios when we use RAP or recycled content in our payments. And to give this in an example again from another LCA application that considers RAP in a complete life cycle. And in this example, we use mixes that contain several levels of ABR, RAP and RAS. And in this case, we can see in the first box of this plot, during the material production stage, we can clearly see some savings in the material and production stage. And the second and third block in this figure that shows the energy savings or the extra energy required during the use phase of a payment. And this use phase energy consumption or emissions are resulting from basically roughness of the road with the payment scenarios deteriorating faster or slower with the use of RAP. In the case of scenarios that varies from 11 to 17 years, with an average service life 15, for low volume roads, we can clearly see that initial benefits for low volume roads can be offset by a 3-4 year reduction in the service life. And if you look at the high volume roads, you can clearly see it's very sensitive to any change in the payment service life. And initial benefits for high volume roads can easily be offset by even less than a 1 year reduction in the service life of a high volume road. So overall, we can conclude from the applications and that the full life cycle analysis, of course, is required and essential to evaluate upfront benefits and then to compare them with the potential future trade-offs by using a RAP in our payments or any other recycled content in our payments. And we may say that excessive use of recycled materials may result in accelerating payment deterioration, and the savings occurring during the production stage can be neutralized by reduction in IRI or additional maintenance and rehabilitation activities that require more energy consumption during the use phase. The second most commonly used end-of-life option that will be spending the remaining part of our presentation will be the full depth reclamation, FDR. And in the FDR, just to give you a definition of FDR, the existing asphalt pavement and a predetermined portion of the underlying layers, which may include base and sub-base, are uniformly pulverized and blended to provide a homogeneous material. And the depth of recycling for a typical FDR application can be within the range from 6 to 12 inches. And just to give you a timeline of different activities which was discussed at the beginning of this webinar, we have various other in-place recycling techniques which are hot in place, cold in place, and full depth reclamation. And full depth reclamation is the one that is usually conducted when the payment approaches to its terminal service life. And at